Everyone, so we're here for Chapter 6, Work and Energy. To talk about that, first we need to go over a different way to describe vector quantities. And so what we have here is what we call a scalar dot product. Because in the past, what we've been able to do is add vectors, tail to tip. We've been able to subtract vectors the same way to find resultants. But we really haven't been able to multiply vectors yet. And that's really what we're going to try and do here. With a scalar, the reason we also call it a dot, or if I go back and forth between those two, is that little dot there between A and B is for multiplication. So I'm taking vector A, I'm multiplying it by vector B, and that little dot is in the middle to represent multiplication. And the nice thing about this is when I multiply two vector quantities, it actually does produce a scalar quantity, which is very helpful for us and something you'll really like in this chapter, that we don't have to worry about direction as much as we've had in the past, because we're going to be doing a lot of dot products in here, and the dot products just give you a number in the end. So a couple rules that you have to do here. What we're trying to do is determine the amount of force in the direction of a displacement, or it could be any vector in the direction of another vector. And I'll show you what I mean by that. The way we write it is A dot B, or you take the magnitude of vector A and you multiply by the magnitude of vector B, and you multiply that by the cosine of phi. The cosine of phi. Phi is the angle between vector A and B. So what we can do is we can take A, if it's got x, y, z components, and multiply them by the x, y, z components for vector B. And the nice thing is when you take dot product of unit vectors, I dot I gives you 1, a j dot j gives you 1, and a k dot k gives you 1, which means that those three combinations are the only thing you can multiply. You can only multiply ax by bx, or ay by by, or az by bz. And the reason for that is that that angle phi is 0 when you have two vectors in the same direction, both in the I, both in the j, or the k. So when you put cosine of phi, cosine of 0 is 1, so you just get the magnitude of those two vectors multiplied together. All other combinations, if you do an I dotted with a j, those are at right angles to each other if we look at our xyz plane. So if I did an I multiplied by a j, I would get nothing, because the cosine of 90 wipes out to 0. So let's try a couple examples here and show you what I mean by doing a scalar dot product. Okay, so let's say we have two vectors. Well, vector A here with a quantity of 4 in the I direction, minus 7 in the j direction. And we have vector B, which has a magnitude of 5 in the I direction and 3 in the j direction. So if we follow our rules, what we want to do is find the dot product of multiplying vector A times vector B, or vector A dotted with vector B. So the way you can do that, if you want to write A dot B, what you're going to do is you're going to take the I components and multiply them together and add them to the j components. So the I components are 4 times 5, and we're going to add that to the j components, which is negative 7 times 3. So if you do that math, you've got 20 plus a negative 21. A dot B ends up being just minus 1. So you go, okay, great, I'm able to do a dot product. I can multiply numbers together and add them. So what? What does that do for us? Well, we have to visualize where this is. Vector A is 4 in the x direction and negative 7 in the y direction, so it's down in the fourth quadrant. Vector B is in the first quadrant, 5 to the right and 3 up. So what we're really seeing here, vector A off in this direction, and we're seeing vector B up in the first quadrant. So we've got vector B, and we've got vector A. And what we've done is we've multiplied those two vectors, and it gave us a scalar quantity in the end. It may not make a lot of sense right now why we're getting a scalar quantity in the end, but when we make A and B actual physical quantities that we use in physics, a whole lot of sense once we get to that. So what we've just done there is we've got A dot B. The goal would be to find what is the angle between these two. What is that angle phi that we want to know between A and B? So what we have to do is we have to take A dot B and we multiply A dot B by the magnitudes of A and B, multiplied by the cosine of phi. So what I need to do is now multiply the two magnitudes of vector A and vector B together so that I can get a number to move to the other side and find my angle. So how do I get the magnitude of vector A or vector B? Well, magnitude would just be how long is that vector in the two-dimensional space that we have here. It's 4 to the right, it's 7 down. So if I wanted to find that magnitude, I'm going to use Pythagorean and square each of my values, take the square root, and I get the magnitude of A to be about 8.06. And I get the magnitude of B, if I do the same thing for B, to come out around 5.83. So all I'm going to do is put the magnitudes in for A and B down here, and when you multiply those two together, you get about 46.98. Again, just giving you another number there when you multiply those two, the magnitudes of those quantities together. So we want to solve for phi. If I want to get the angle phi by itself, I've got to get rid of this A times B. So I'm going to divide it to the other side and do minus 1 over 46.9 equals cosine of phi. If I want to solve for phi, I just do the inverse cosine of that setup. And what it gives you is that this angle phi is about 91.2 degrees. So make sure you can do that math and get the same answer that I get here. So that means that A and B are separated by about a 91 degree angle, which just in my rough sketch here, A and B look like they're about 90 degrees apart. Maybe a little less, maybe because I didn't do that to scale. So that's what we do with vector quantities. We want to figure out the angle between vectors, or if I was given the angle, you might be able to figure out the magnitude of a vector in its I and j components by doing all the math in reverse. Another thing that they're going to ask you is how much of vector A is in the direction of vector B. And it might be written like this: how much of vector A is in the direction of B? Well, to do that, you've got to take A dot B, which we already know is -1, and divide it by the magnitude of vector B. So if I take the magnitude, -1, I divide by the magnitude of B, 5.83, that tells me that 0.17 is the amount of vector A pointing in the direction of vector B. What that could mean that if I project vector A on to vector B, kind of make a right triangle there, this is what I just solved for right here. I just solved for the amount of vector A in the direction of vector B. Like we said, that quantity comes out to -0.17. They can ask us the reverse too, be like how much of vector B is projected in the direction of vector A. So that means you do the same thing. You do A dot B, and now this time we divide by the magnitude of vector A. So in doing that again, that's -1 divided by 8.06. That gives me about 0.124 of the amount of vector B in the direction of vector A. So again, that's what we're talking about, how much of vector B is actually projected along vector A here. Again, I didn't draw that to scale. There's some properties of scalars that the book gives you here. It says that if A and B are perpendicular, then A dot B gives you 0 because the cosine of 90 is 0. If they're parallel with each other, that's what we want for dot products. We want two vectors to be as parallel to each other as possible. So that's why we get cosine of 0 to be 1. And A dot B is 0 if vector A is 0 or vector B is 0, or if they are perpendicular. And they give you a couple other rules down there for dot products. But here's what I was talking about with vector A and vector B. You can see in that top drawing, you've got those two vectors, and there's a certain angle between the two of them. If I want to know how much of B is in the direction of A, all I need is that component, that piece there. Yes, you can use the right angle geometry and use the cosine of our vector B to see how much is projected into vector A, and the reverse over here, how much of A is projected in the direction of vector B. So just like we did in that first example, here's another example that I would like you to try. Find the angle between vector A and vector B here. You've got A equaling 3 meters in the I direction, 2 meters in the j direction, and vector b is 4 meters in the I direction and negative 3 meters in the j direction. Find the angle between them using the rules we just did in our first example, and then I'd like you to find how much of vector A is pointing in the direction of vector B, or A sub B. So try this example, and I'll throw a solution up here after you work it out. So take some time now to work it out, pause the video, see what you get, and come back and I'll show you the answer. So here's your solution. A dot B, you're going to multiply the I components together, so that's 3 times 4, gives me 12, plus 2 times 3, gives me a minus 6, so that means A dot B is just 6. So that's nice and easy for you if you're ever asked, what is the magnitude of vector A dotted with vector B? Now it wants us to find the angle between them. So I have 6 is equal to the magnitudes of A multiplied by the magnitude of B times the cosine of phi. Well, if I look at my setup here, vector A's magnitude is 3 squared plus 2 squared, so that's 9 plus 4, or 13, so this is the square root of 13. And for the other one, I've got 4 squared plus a negative 3 squared, which ends up being a 3, 4, 5 triangle. So if I take the magnitude of vector B, I'm going to get 5. If I'm going to solve for phi, I'm going to take 6 divided by whatever the square root of 13 times 5 is. Comes out to about 18.03 equals the cosine of phi. Inverse cosine of 6 over 1803 gives me about 70 degrees between those two vectors. So that's how we solve for the angle.